Hello, my students. I want to tell you really well done on your videos. You really show that you understand the Wilson cycle, and I'm very proud of you. I've had a lot of students that struggle with it, and so far you're understanding it very well, and you're not just memorizing it. I am very proud of y'all. I can tell that you don't just try to memorize, but that you are trying to understand, and I very much appreciate when my students work to understand processes, because that's what you need to do for the rest of your life. You won't just be memorizing things the rest of your life, right? You're engineers. So I'm proud of you for thinking, understanding the process, and being able to explain it back to me. Very good. So I wanted to let you know that there's just one thing that I wanted to correct on the Wilson cycle, and it was real easy. Don't worry about it too much. But there's a difference between stage. Now let's see if I can do it from my head. A, B, C, D, E. So there's this difference between stage E and stage G. Okay? So in stage E, we've got ocean crust going under ocean crust. In stage G, we've got the ocean crust specifically going under continental crust and making volcanoes through the continent. So let me show you that here. This is the opposite direction of the drawings, but it'll just show you the idea. So we've got the convection currents going, right? They're going opposite ways. Oh, I shouldn't have done it quite like that. Let's change that a little bit. I'm used to doing it. All right. They're going like this. And the ocean crust is not going under ocean crust at this point. It's going to go under continental crust, where it will start to warm up and melt. Let's see here, good multicolor, right? And go through and make volcanoes through the continent. So this is continental crust here. And this over here that's gray is the oceanic, the mafic oceanic and the felsic to intermediate continental crust. That's really important to separate those two because it will make different types of minerals based on what was melting and how it was being formed. Okay, but you did really well other than that. That was great. Get your credit. Just go ahead and get this direction part for stage G. Okay, this is stage G, and in stage G, the ocean crust is going to go underneath the continent, not ocean under ocean. There's a difference there. Maybe I'll ask you guys later to do a video to tell me you did great finding similarities. Wow, well done. I would also say B and C, stage B and C, are similar. I have never had students say A, D, and I. I've seen students say A and I. Never saw anyone say D is like A and I, but you are correct. They are all, yeah, well done. Very well done. I'm very proud of you for that. Yeah, and B and C are similar because they're both rifting, right? So B is the beginning of rifting, and C is when we still have more ocean crust being formed. So you could put those two together. Similar processes, right? All right, great. I'll think on whether I might need to teach through again on convection cycles in the mantle. But I am going to go ahead and move on to a completely new, oops, let's do this. I'm going to make sure that my video and everything is synced, so I'm going to do that here by going 1, 2, 3, 1, 2, 3. It's just how I sync my videos. So we're going to change over from big worldwide processes, huge processes, down to molecular processes. Woo! Big change, right? Now we're going to start talking about how do these minerals form, and then out of these minerals, how do rocks form. It will help us to understand magma, melted rock, how it acts, how it behaves, and how it becomes igneous rock, and how it creates different chemistries of rock. All right, so I I haven't had these slides in the other ones, but it's just a good slide to remember. Remember that geology is a visual science. It means that you have to be able to kind of see what's going on. That's why you have to draw all over the board. You have to visualize. This is true at the large scale. This is also true at the molecular scale. The ability to visualize what's going on will help you understand so much more. So if you're having a hard time seeing what I'm saying, then you need to email me questions, okay? But so far you're doing great. All right. I used to have this, right? You remember this? Be the hero, ask the questions. Just email me questions if you have questions. Go for it. All right, definition of a mineral. Oh, again, how many times do I wish I was right there and could just interact with you and see? Do you remember the definition of a mineral? Get ready to write it down. Maybe try writing it down right now. What? 5 parts from geology class. 5 parts. Definition of a mineral. The mineral must be, what's the first part? Oh, come on. Natural. When I say natural, I mean geologists say, if you make it in the lab, it's not really a mineral. Whatever. I don't care too much about this part of the definition. Next part is extremely important, though. The second part is that it has a chemical composition, a unique chemical composition. One mineral will have one chemical composition, another will have a different chemical composition. Some minerals, you can have 2 minerals that have the same chemical composition but have different physical properties. That's possible because of the way they form. That chemical composition. So, example, sand is SiO2. Quartz sand. If you go outside and pick up sand, most of that will be the chemical SiO2 quartz. We'll run into more here. My brain's not coming up with some quick ones. Inorganic. When we say inorganic, we just mean that we don't have long chains of carbon. When you have long chains of carbon with other things like hydrogens and oxygens on them, we call this an organic molecule. Some minerals are formed through organic processes, but they still are inorganic because they don't have long chains of carbon. So that's a not mineral. Solid. It's not a mineral if it's a liquid. It's not a mineral if it's a gas. Very simple on that one. And the last one is crystal structure. By crystal structure, I mean that there is a specific shape. So that specific shape could be a cube. It could be a hexagonal shape. I'm not good at drawing, you guys. There's a reason I'm a scientist. There we go. Many different types of shapes, but it's that crystal structure is going to be that same shape over and over again. In this part of this class, as we're getting more advanced in geology, we're going to focus on 2 aspects, and it all really boils down to one. So chemical composition and crystal structure. And we're going to find that the crystal structure is actually what it is because of the chemical composition. So in reality, a mineral is a specific type of chemical. All right? A mineral is a solid, inorganic, naturally occurring chemical with a crystal structure. There you go. But it's a chemical. That's the most important part of all of this. We're going to talk a bunch about chemistry today. So go ahead and pull that chemistry up in your head. So crystal structure and chemistry are related. To be able to start understanding all of this, we need to do some review. So crystal chemistry. You don't know crystal chemistry yet. You're going to know crystal chemistry. We have to review some basic chemistry. I'm going to go very fast through all of this. If you don't understand atoms and protons and electrons and molecules yet, how can you almost be graduating? You know these things already, so we're going to go really fast. So you need to understand elements, matter, atoms, elements, ions. Pick those up in your brain. The periodic table. Bonding and valence might be something you haven't covered too much in other classes. I'm not sure, but we'll cover some of that today. So an atom basic unit of matter. I'm not going to have you write this stuff down. Good grief. You know it. Right, keep going, Carrie. Element. An element. You know what an element is. It's the matter that's made of only one type of atom. So there we've got some mercury, we've got some carbon, we've got some gold. Elements, right? Basic elements. Periodic table of elements. You know the periodic table of elements. This is just for your brain to wake up and be refreshed. Here we go. Particles in an atom. You know all of these. Protons, neutrons, electrons. Protons plus neutrons equals the nucleus of the atom. Orbitals. I keep kind of stumbling over this because I'm not sure if this is the way it's taught anymore, but the layers of electrons around the atom. I know that they really are just clouds, but they tend towards a certain level of valence, right? Okay. Just go fast because there's a lot to cover. Atoms of the same element, remember, always have the same number of protons. They can have different numbers of electrons. So protons are constants in an element. If you change the number of protons in an element, you are changing the element to another element, which can happen through nuclear processes. We're not going to go there. All right, an ion is what happens if I've got an atom and I add an electron or I remove an electron. We're going to change the charge on that atom, and at that point it will be called an ion. It will either have a positive charge because it's removed an electron, or it will have a negative charge because it's added an electron. Right, so if it's positively charged, we can have positively charged atoms and negatively charged atoms. If we've got a positively charged atom, we're going to call it a cation. So this is the part where you really do need to start remembering and keeping track, because we're going to talk about these ions a good bit. Cations are positive, anions are negative. So here's another example of a mineral. This mineral is table salt, right? But the real name for this mineral is halite. And it's made out of a cation, a positive sodium, and an anion, a negative chloride atom, bonded together to make one mineral. One naturally occurring naturally occurring solid with chemical composition and crystal structure. There you go. All right, so we can again remove an electron and make it a positive charge and get a cation, or add an electron and get a negative charge and it'll be called an anion. Why is this? Again, because electrons have negative charges. So if you've got a stable atom, you remove the negative charge, it will become positive. You've got a stable atom, you add a negative charge, it will become negative. Valence is the charge of the atom because of those electrons being added or removed. So we can have positive valence or negative valence. This is an interesting chart right here. Oh, do I have this one? No, I'll animate it later. So on this chart, we can see that we've got certain charges. So there's boron, and it tends towards having a positive 3 valence. Let's see here, fluoride tends towards having a negative 1 valence. When an atom or something, like a mineral, something goes through the process of adding an electron or removing an electron, we're going to talk about oxidation and reduction. So oxidation happens when an atom loses an electron. So I can take iron plus 2 and remove an electron and get iron plus 3. Or we can do, so that's oxidation. When I'm talking about oxidation, I'm talking about the removal of an electron. Oh boy, and now it's getting dark outside, so suddenly it's getting very grainy in here. Let me, all right, it's a little better. So we can have oxidation, which is the loss of an electron, again. create a positive charge or to increase the positive charge even. We have reduction, where electrons are added and we get a negative charge as a result. Most atoms are unstable, electrically unstable, because they do not have a full outer shell, a full outer electron shell. So the outer electron shell, most except for the inner shell, can only have 2 electrons. Most of those shells can have up to 8 electrons. And when an atom has a full outer shell, it's either it's a noble gas. So a noble gas itself has 0 valence because its outer electron shell is full. It doesn't want to give up electrons. It doesn't want to take electrons. So it's just stable. Noble gases. These are all our noble gases. Noble gases are stable electrochemically. Elements that are, most elements are not noble gases, right? Everything to the left of that line is not a noble gas. And they have either an outer shell that has just 1 or 2 electrons in it, or an outer shell that's missing a couple to be able to get to what is called noble gas electron configuration, or that outer shell being full of electrons. So what that element will do, will be to give up electrons or to take in electrons to become full in that outer shell. When that happens, they'll ionize. They'll either become anions with a negative valence. So oxygen has given up 2 electrons. Those that had an outer shell that had 2 electrons, and then inside of that shell it had 8 electrons. It gives those 2 It has 6 electrons in its outer shell. It takes in 2 electrons to become 8 electrons and ends up with a negative charge. Or we've got the cations on this side that have lost electrons. So lithium over here had an outer shell, like I was just saying the wrong way, had an outer shell with 1 extra electron. It gives that up so that the next shell down will be just 1 solid set of 8 electrons. At that point, we can get some attraction, ionic attraction between the negative and positive valences. Minerals are stoichiometric. When we say stoichiometric, we mean that they are electrically neutral. So here's a good example. We've got positive charge equals a negative charge. So that the whole mineral, this is hematite, iron 2, oxygen 3 is hematite. This iron has a positive 3 charge, and there are 2 of those atoms. So we'll have a positive 6 charge on this side, and negative 2 charge on those oxygens, and 3 of those atoms of oxygen give a negative 6 charge on the oxygen side. Negative 6 plus positive 6 is going to be a total valence of 0. So this is a stoichiometric mineral. All minerals are stoichiometric. All minerals must be stoichiometric. So minerals are going to bond for 2 reasons: to become stoichiometric and to cause all of the elements within the mineral to each have a noble gas electron configuration. In some way or another, they're going to all try to get to a full, every atom in the mineral has a full outer ring of electrons, outer shell of electrons. So chemical bonding, it's the way that electrons hold atoms together. Those electrons can be doing different things. So types of bonding in a mineral, the electron can be shared. So we've got 2 atoms here, and they're going to share. So here's 2 atoms, and they're going to share an electron. be held together by that same electron. They're going to hold together because they have the same electron. Can have an ionic bond where one atom gives up an electron to another atom, and now this atom that gave up the electron is covalent. Oh, sorry, it's not covalent. It's a cation. It's positive, and this electron, this atom that took an electron is negative, and so now they are statically. They're going to have positive and negative charges that are attracted to each other. Metal bonding. This is really cool. I like this. Metal bonding. You've got atoms that are all sharing electrons. So all the atoms are just, the electrons just flow through the whole thing. And this is why we can use wire made of metal, like copper, to transport electrons. So in this case, this is an electron, right? It'll just keep flowing through. And van der Waals bonds are this static type of bond. If you take a balloon and you rub it with a cloth, and then you hold it over some pieces of paper, if the air is dry, the paper will stick to the balloon. It's an electrostatic charge thing, similar to ionic bonding, but a little bit different. And it's a very weak bond, so you can really easily take that apart. Same thing for the minerals with van der Waals bonds. Easy to take apart. Minerals can have just one type of bonding, or they can share two different types of bonding. So they could, like a halite, salt is ionically bond, and that's just it. Metallic, galena is a mineral that has just metallic bonding. Diamonds have just covalent bonding. But some minerals have more than one, so silicates have both ionic and covalent bonding. Sulfides and sulfosalts, sulfides are the more recognizable ones, have both covalent and metallic bonding. All right, let's look at the different bonds. Covalent bonding, again, the electron is shared between, so one or more electrons are shared between two atoms. I've got an electron here and an electron here that are both being shared by these two atoms. Because both atoms depend on these electrons, this type of bonding is very strong. A great example of this is diamonds. Diamonds are very strong minerals, and the reason that they are so strong is that they are sharing all their electrons. No, most of their electrons. Metallic bonding. Again, the electrons are moving through the metal. A good example would be copper. These are excellent conductors of electricity and heat even, and they have a strong bond. It's hard to take this bond apart. Ionic bonding, you've got, again, two atoms. One is going to give up an electron, so this is a sodium, say this is a sodium atom, and it's going to give up an electron so that its outer ring now gets that one out of there, and now the ring down has exactly eight electrons in it, and the chlorine had 7 electrons, and it's going to take in that electron from the sodium so that it now has 8 electrons in its outer ring. But now chlorine is going to be negatively charged, and sodium is going to be positively charged, and the atoms are going to be drawn together. Bailey, that's my shoe. You cannot have my shoe. I should have put my shoes away, huh? The adventures of owning a dog and making a video. Bailey, can you bring me my shoe? No, thank you. Oh, there you go. Let's play with this ball, huh? Now I need the balls for now. Let's play with the bug. Woo, the bug! I'm gonna go get my shoe. Ah, there you go. There's the bug. Bailey. Gonna give me your bug? Where's the bug? Give me the bug. Give me the bug. Yep. Right. Two charges. Attraction. Opposite charges. This type of bonding is very, it's low strength. Many of these types of minerals can dissolve in water, so we add water and it breaks that bond. This is the most common type of bond for minerals. Most minerals are bonded with ionic bonding. That's why you can dissolve almost everything. Water is really good at dissolving things. We're going to build the molecule with oppositely charged atoms over and over again, oppositely charged ions. Sodium chloride would be an example, halite. Chloride again with that negative, and sodium with the positive. So positive, negative, positive, negative. There we go. I want you to notice something here. The cations versus the anions, which are the large elements? Cation versus the anion. The cations are again positive, the anions are negative, so you can see that the cations have a much larger radius or diameter, and the anions have a smaller diameter. Keep that in mind. All right, the last type of bonding, again, is van der Waals bonding. These are molecules that are being just attracted by opposite charges, similar to ionic bonding, but it's not giving its electrons or taking electrons. It's just this really weak force that's pulling them together. Very low strength bonds. Good examples are graphite and mica. All right, let's build some minerals. So again, the definition of a mineral, it's naturally occurring. It has a chemical composition, which is, this is important to me that you know this. It's inorganic, because we'll never talk about organic molecules in this class. That's as much as you need to know. We don't really care about that part. It's a solid, but all crystals are solid, so these are the really important parts of the definition of a mineral. You need me to throw something for you. You want a ball? Whee! Go play with that. You like balls. Go get it. That's not very interesting. How about this? Whee! You need me to go get the toy that you dropped already. Or how about this? That's going to be fun. Okay, go get it. All right, so let's look at the crystal structure of minerals. Crystals are going to form through repeating bonding of elements. So we're going to add an element, add an element, add an element in a repeating structure over and over again. You need me, don't you, dog? You need me to stop being a teacher at the moment. He's just fine until I'm talking to myself and talking to the video. All right, so in this case, I've got lead. I've got sulfur and lead repeating. In this case over here, I've got halite. Oh, sorry, I've got halite made of chloride and sodium chloride repeating back and forth. But not all minerals have this same structure. So this particular structure, it's what we would call cubic structure. It's going to just keep forming by adding each element at 90 degrees from the last. Same thing over here. Adding each element at 90 degrees from the last. Mineral classes are going to be based on mineral chemistry. So we've got anion groups and cation groups. Anions are anion groups and cations are cation groups. So what's an anion? What charge does an anion have? Is it negative or positive? Anions have a negative charge. What's an anion group then? An anion group is going to be anywhere we've got a group of elements that when they come together, they become negative. You don't care. Come here. Just sit with me while I'm teaching. How's that? Just be a total distraction and be cute, huh? All right, so here we go. We've got sodium +1 means cation or anion. It's a cation. And chloride has a -1 charge. So it's an anion. They come together and they build sodium chloride or halite. In potassium feldspar, I've got a group of elements, potassium and aluminum, that come together. And when they're together, they're going to make a positive charge. And then I've got, silicon and oxygen, and when they come together, they're going to make a negative charge. So this is a cation group. This is an anion group. All right. We're going to classify our minerals based on their anion groups, their endings. All right. So the main the main anion group that's out there, 92% of Earth's crust has a silicate anion group at the end. These are really interesting. They can have any number, not any number, but a range of different numbers for silicon, a range of different numbers of oxygen. And because those two change, their charge will change, but their charge will always be negative, except in the case of quartz, in which case it will be just 0. Then we've got the remaining 8% of all minerals in the Earth's crust. Oxides have a -2, they're -2 anion. Carbonates, CO3 -2, that's an anion group, right? Not just an anion, but an anion group. Sulfides are S -2. Sulfates, SO4 -2, so that's again an anion group. Phosphates, PO4 -3. Halides can be ending any mineral that ends in chloride, fluoride, or bromide. And then native elements are minerals that are just made of one element. So an example would be gold. Gold is one element. The mineral is made of one element, gold. Or silver is made of silver. Or copper is made of copper, right? Sulfur is made of sulfur. Crystal structure, this is again going back to the shape. Minerals have symmetry. This means that the atoms are going to continually connect in 3 dimensions in a repeating pattern over and over again. They're going to make a specific geometric shape for each mineral type. And they have symmetry. So the shape, you could see, if you look at a face of that mineral, you could fold it or turn it and see that same shape again. So one example would be a cubic or a square. One side could have a square shape. That square can be turned 90 degrees. It could also be cut in half and make the same shape on both sides, a triangle, or it could be cut in half this way and make the same shape on both sides, a rectangle. We could have a rhombohedron where the whole shape could be turned 180 degrees, or it can be cut in half one of 2 different ways. You could have a triangle, and it could be turned 60 degrees, or be cut in half this direction, or this direction. And we've got a hexagonal shape. It could be turned, in this case, 180 degrees, but really 30 degrees. And it can be cut in half and along from corner to corner like this in 3 directions, or from edge to edge like this in 3 directions. All right, so all minerals have this symmetry thing going on. They have this repeating crystal structure. So a question for you, I think I've asked you this before in geology class. Is ice a mineral? Let's test it. All right, so what's the definition of a mineral? First of all, it's naturally occurring. Ice is naturally occurring. It has a chemical composition. Does ice have a chemical composition? Answer for that is yes. What's the chemical composition of ice? H2O. You are really annoyed, aren't you? You really want my attention and not me talking to nothing. You're just so jealous. All right. Let's see here. It has... it's not organic, it's inorganic, right? And we don't have a long chain of carbon here. It is, it's a solid. Is ice a solid? Yes, right? And it's got crystal structure. Does ice have a crystal structure? Does it have symmetry? Yes. If we look at a snowflake, we can see that it has 3 lines of cleavage, or lines of crystal faces that are parallel to each other at 60-degree angles. You gonna go? You really want to play? Oh my goodness, this is not the time. Here we go, go get it. You want to play with me, huh? All right. So this ice has, you can see inside of the ice, 60-degree angles. And you can see ways that we could fold it or cut it. So I could cut it in half this way. I could cut it in half this way. I could rotate the whole mineral, 60 degrees, and I get the same pattern, right? So yes, ice is a mineral. Crystals, because of this repetitive nature, they're going to build faces for themselves. They're going to build flat faces. They're going to be smooth on the outside. There are going to be two types of faces. There's either going to be a crystal face that's exactly the edge, the very outside edge of the mineral. Ooh, I bet I've got some minerals up here I can show you. Should have thought about this. Ooh, yeah, there we go. That's another good one. Ooh, this one's the best. This is excellent. I wonder if you can see this. All right, so in this mineral, see if I can get really close there. No, I probably can't quite see it. In this mineral, we've got repeating faces. Anytime you see shining, that's going to be a face. And sometimes those shiny faces are going to be larger than others. And these particular faces are cubes. They're going to make squares. There's a good one right there. Yeah. So we've got repetition as a square right there. Cubes. And then this one, see how it gets really shiny around. There we go. It's real flat right along there so it can reflect the light really well. That's crystal face. Sometimes they're not as shiny as others, depending on how smooth they are, but usually they're pretty smooth. Cleavage faces are where they break, and they're really flat. Those can be really smooth. Also, they can be less smooth as well, depending on what kind of bonding they had. Sometimes if the bond is stronger, that means when they break, they're not going to have really flat breaks. They're going to have kind of rugged breaks, rugged faces. So how are these crystals going to form? We've got, temperature. So let's talk about controls on forming crystals. Actually, this might be a really good point. Think for a second. Stretch, get up, breathe, move around a little bit. Be like my dog who needs to move and play. Bailey, go get it. All right, go ahead and sit back down. You get stretched out. Good. All right, let's move on. All right, so what are the controls on crystal formation? The first control on crystal formation is going to be temperature. So temperature inside the earth is going to be hot, but some places it's going to be hotter. Some places it's going to be less hot. It's all going to be hot, but there are going to be places that are hotter than others. If crystals are forming at high temperatures, the elements around them will be moving faster. And so think about, you've got elements that are moving really fast. High temperatures usually have a simple structure. Oh, this is not going to talk about size. I was thinking we were going to go into size. I was like, this makes no sense. All right, just a structure. Simple structure versus complex structure. We're going to get our simpler structures, especially for silicates. This is really going to apply to silicates. Simpler structures for silicates, when the elements are moving very fast, it's going to be hard for them to bond and make larger structures. So we're going to get our simplest structures at high temperature. If the temperature is lower, those elements will be moving slower, and they'll be able to bond to each other. They'll connect and build larger, more complex structures. Not necessarily a larger mineral, but just larger, more complex structures. Chemistry is going to control the way that crystals form. So if you're making halite, which is again sodium and chloride, and you're adding sodium chloride, sodium chloride, sodium chloride. If you run out of sodium, you can't add the next chloride. You're done. So the elements that are available in the liquid around the forming mineral are going to determine what minerals can form. They're like ingredients making any kind of food. The last control is time. If a mineral has a lot of time to form, it will grow larger crystals and they'll have better structure on the outside. And if it has a short time to grow, they'll be smaller. It's like pretty much anything in the world. All right, crystal growth video. We're going to pull out here and go to Dropbox. All right, so I want you to watch how these crystals form. This is really interesting. You can see, pretend these are elements that are moving on. They're really not elements. They're actually small crystals that have already formed. But they're being drawn in. You can see the little paths that they're following to become part of these crystals. And these minerals, as they form, have these smooth edges on them. That pattern remains the same. It's like it's just getting larger and larger and adding to its edges. It's continuing to grow over time. More and more is being added over time. And I think that was the end of the video. No, not quite. I always get fooled when it stops having little bits of pieces move around. But you can see how pieces are being added in, pretend those are elements being added in. And those shapes stay the same that whole time. Was it going to replay? No. There we go. All right, so we've got, it doesn't hurt to watch it one more time. All right, so we've got certain shapes with more and more elements being added over time. Each of those shapes that you see, that rod in the bottom right, that kind of dagger looking thing at the top, the blue shape that's growing, those are each minerals growing out of a liquid with elements that are being added, one element at a time. I'm going to show you another video. I don't know if I did this before I took the break, but another video where we've just got one drop of liquid and one element at a time. It's down to the elemental level, watching how that mineral is growing. Creating these same shapes, just making them larger and larger. So the more time that we have, the larger the minerals can get. Does it let me? No, that didn't. It just exported a picture. That's the video that I need to show there. Oh, interesting. Hello. Wonder what happened here. Let's just exit out of this and go back into it. All right. All right. We're going to have two different sizes for crystals. We're going to have phaneritic sizes for crystals in a rock. We'll have aphanitic set sizes. So phaneritic, I want you to think of an elephant for phaneritic. These crystals grow in hot environments. They grow very slowly and they grow very large. So think of a large elephant maybe living in India or something in a hot environment. These crystals get very large comparatively in size. Aphanitic crystals are grown in a cold environment. Because it's cold, they become solids much faster. The minerals end up being quite small. So think of a little mouse in the winter in Mongolia where it's really cold. Small minerals that grow, then it moves really fast, right? Elephants move slowly, mice move quickly. So aphanitic, small crystals formed really quickly in a cold environment. So to be able to compare these two, did I make that animation? There we go. I want you to notice that both of these pictures are at the same scale. Look at the 1 millimeter here and the 1 millimeter over here. Over here we've got fine-grained aphanitic crystals. So these are aphanitic. And these are phaneritic crystals on the right. Look at that 1 millimeter. Is the exact same on both sides. Just very, very large crystals that grew slowly in a hot environment and grew very large. We've got small crystals. These are exactly the same minerals that didn't get as large. It's not like I zoomed in or anything. This is actually the same size piece of rock, just or same magnification. Okay, sorry for the sudden stop, but I realized that I was at a good stopping point. So even though I kept teaching, I cut off the end of that video and decided to stop here for today. So thanks for following so far. Next week we'll start to actually chemically build minerals into what's called a unit cell. We'll learn a little bit more about the chemistry and physics of making minerals. I think this is plenty of information for now. There's some good review in here, but there's also a lot of new information. So do your quizzes like usual. You can go ahead and write whatever you need to as you're answering questions, write on the board if it helps to answer some of these questions, or draw on the board if it helps to draw. That's just fine. I wanted to point out, what question was it? In set 3, question number 2, before you do answer number 2, stop the video, write with the video paused, write from your notes the chemistries of all of the anion groups on the board. Then start recording again and give me the names of each of them. You don't need to memorize the chemistries right now, and I probably won't make you memorize the chemistries at this point. So I want you to at least be able to give me their names. That's it. So again, you don't need to memorize the chemistries, just memorize the names and know which name goes with which chemistry. All right, that's it. And then you'll have one question that you're going to email me. Set 5 is really just email me an answer about aphanitic and phaneritic minerals. And that's it. You guys are doing great. Proud of you. There's my dog shaking everything. Here, say goodbye, Bailey. Come here, Bailey. Say goodbye. Goodbye, students in Mongolia. Oh, you're going to give me kisses. I love you too. You miss me? Am I making boring things? Should we play now? Okay. Goodbye.